Thank you very much for the introduction, and hello everyone. In this talk I will speak about light and especially how we can obtain the light from the real world for our computer applications. So let's define the problem first. We have an image of the real world, for example like one which we see here. We see that's a picture with some marker for tracking and with a 3D printed real dragon. So there is just real world here. And we would like to estimate how the light situation in this scene looks like. So we, as the humans, we can always guess where the light comes from. If we take a look, we have a feeling the light comes from the back, a little bit more from the right. But now the question is, can computer systems estimate it? Or can we develop some systems which can actually capture it with some additional devices? And how can we represent this light then? So ideally, we would like to have, for example, the directional information about the dominant light direction in the scene. That can be a single light direction coming to our point X. And most often we represent this light information as the light coming from infinity. So we actually do not care too much about spatial variation of the light, but we especially care about directionality of the light. So let's say we want to estimate the main light direction of the light coming in this scene. Or we can make it a little bit more complicated, and we can estimate light coming from all directions, represented in this kind of a light probe image, where every pixel we represent one direction of the light, and we store the radiance value of the light coming from this direction. And that can describe very well the directional information of the light in the real world. And what we can use it then for example, for rendering in augmented reality, where we have this kind of a scene, that's the same image, and we want to render now the two digital objects here, the dragon and the glass monkey, with a consistent light, as it is in the real world, to have consistent shadows and consistent reflections as real objects. Now let's come to the talk, how can we do this? And before we ask also why can we do this, so first application is augmented reality, where we want to insert digital objects into the real world images, as we can see here. This cube here is digital, is virtual, and these two cubes are real. And what we would like to achieve is the light interaction between the real world and the virtual objects. So what we can see in this virtual sphere, it does reflect the light from the real world, and also this virtual cube is casting the shadow to the real table which is below it. But there are also some other applications, for example, scene understanding, which we see nowadays very often with the autonomous driving. We would like the cars to be able to understand the scene. That includes the objects, but as well as the lighting situation. Or we can do scene relighting if we want to change the light in the pictures. So now let's come to the point, how can we do this? And we have three categories of methods which can achieve this light capturing or estimation. And the first one is we can capture the light by using some additional devices. An example of that is a camera with a fisheye lens like this one, which can capture the very wide angle image and capture the whole upper hemisphere of light coming to this camera. And that one can be used in real time, either with the computer vision methods to analyze the dominant light direction, or directly with the image for the image-based lighting. Or we have a second possibility. We use normal photography of this kind of a mirror sphere, and this mirror sphere reflects all the light coming from all the directions in the world. That's another second possibility. And the second category of method is we can capture the illumination with a normal type of camera without a fisheye lens while we move it. An example is our mobile phone camera, and what we can do, we can just rotate it around and capture all the light around us, and we can then use it for rendering or other applications. We can stitch these images together to create also this light probe image. And the third category of method is light estimation, where we have only the individual image, as we saw at the beginning, and we try to estimate from this image where the light is coming from. Let's come directly to the first category of method, which is light capturing, with this kind of a fisheye lens camera. And what we would like to do here, we would like to detect the dominant light direction, so single light ray, and the direction where it is coming from. And what we do to obtain this is firstly we capture the image, which looks like this, and then we try to detect where the light is coming from. For this one, we use some computer vision methods. And first we use thresholding, which is often done to get a differentiating between the bright areas and the dark areas. Then we use connected component analysis to kind of surround these blobs. And then we detect the biggest blob, and we sample it, and that can be our light source. And then we can back project it to our image, and that gives us the direction of the dominant light source, which we can then use for the rendering. Here is an example of augmented reality, which is using this kind of light detection in real time. And what you will see here, there is a real table with real cubes, and there is this virtual glass monkey head rendered. And I'm moving in this video with the light source, with real light, which is being estimated by the fisheye camera. By the way, fisheye camera is a little bit hidden here, but it is there, and it detects this light and uses it in real time for rendering. So you will see how the shadow of this glass monkey is adapting according to the shadows of the other objects. So let's play this. And as I move the light, you see the shadows are moving of the real cubes, and so does the shadow of this monkey, and also this caustic image, that's this light pattern below it. Because everything is calculated in real time, the light from the real world is detected by the camera, hidden here, and then used for rendering. But that was the light direction. What if you would like to capture the omnidirectional image, the image which captures the radiance for all the directions on the sphere? And we can do this, for example, with the mirror balls, or we can use also our camera image. What is very important point here, we need to store and capture the images in the high dynamic range values. And what that is, in contrast to the low dynamic range, which is our traditional 8 bits per pixel per color, which we store our normal images from normal cameras in, high dynamic range should use more bits per color per pixel to store higher variation of information. And the question is, why do we need this? The reason is that 8 bits only provide us with the 256 different values, and if we have such a high variety between the dark shadows here and the bright areas here, and we want to capture all the details, we need more levels than 256. So we either use more than 8 bits, we can use 10 bits, 14, 16 bits, and then we can calculate the high dynamic range image, which is ideally then used for rendering or any other purposes. And now the question is, how can we obtain this high dynamic range image if we have cameras that only capture 8-bit images, like these ones? And the answer is, we can use bracketing photography. So we can take these two pictures with two different exposure levels, and then we can combine them together and calculate the high dynamic range, one final image from all these values, which has good details both in these areas, bright areas, and both in the dark areas. So how can we do this? We use this equation to reconstruct the final irradiance values x for every pixel. And in order to be able to reconstruct this, we simply actually sum up the values, multiply them by exposure time, Ti here. But we need to know one more thing, and this is this f function. So what the f function is, f function maps the irradiance from the real world coming to the sensor to our pixel values, to our 256 pixel values, which we have. And the reason for this is that our cameras can capture a little bit more than just the simple small linear scale. So this is typically a nonlinear function, and if we want to reconstruct this high dynamic range radiance, we would like to know the inverse of this function, which is called inverse camera response function. And the process of obtaining this is called radiometric calibration. And the inverse camera response function typically looks like this, where we have our 256 values of the image brightness, and we can remap it back to the relative irradiance from the real world. And now the question is, how can we calculate this? And the answer is, we can calculate it jointly with the reconstruction of these high dynamic range values of x, and we can do this in the alternative fashion. So we start with a linear function. This f can be linear, like this. We map our brightness values, that's y, which our camera reads, and calculate with this equation. We need, of course, multiple exposures here, and we sum up these images in the sum, and calculate this radiance value here. And as soon as we have it, that's our first estimate, which is not yet good enough, but we can use it now to calculate again this camera response function, the inverse. And once we calculate it, then we can again calculate the new values, and we just alternate these two calculations until our inverse camera response functions get this kind of a nice shape. And then also our radiance values here get much more proper values. So that's the way how we can reconstruct high dynamic range values from the low dynamic range images, and what we typically use in the photography where we want to have the light, because light has can have many more different values than 256, can have really high range. The second category of method is the illumination capturing and stitching by the mobile moving camera. And here we again assume the distant light, so we can rotate our camera, and no matter where we move it, we assume the light is coming from infinity, and we omit the spatial variation of the light. which is actually quite good for the outdoor scenes, not that good for indoor scenes, but we skip that for now. And the way how we can do this, we can use our mobile devices, for example, and we can rotate them, use our low dynamic range images from the camera to calculate the high dynamic range values of the radiance. But one important thing which we need to know is how can we map these images which we have to this full sphere, to this light probe image which covers all 360 degrees of direction. And the answer is we can use our IMU unit, which stands for the inertial measurement unit, in all the mobile phones, which measures the orientation of the device with respect to the gravity and also to the magnetic field of the Earth. So once we get the orientation, we can project these image values with the proper orientation to this image, and we can reconstruct by rotation the full 360-degree panorama in high dynamic range. And we can implement this interactively on the mobile GPU. Maybe you may be asking, how do we do this projection of all pixels or all directions to this light probe image? And the answer is here. So this is the parameterization, how we can obtain the UV coordinates of the image. So that's basically XY coordinates in this 2D space from any 3D vector which we have here. So this is our input 3D vector, omega, and our UV coordinates go from -1 to 1, both in the U domain and V domain. And that means the center is here in the middle, and -1 goes down, 1 goes up, and the same for left and right. And then UV we calculate simply by multiplying x by the magic coefficient R, and y also by the magic coefficient R. And what this magic coefficient R is, we calculate it like this. As you see, it mostly depends on the z coordinate here, and it is actually radius, how far should we go from the center here. And by these equations we can find a very nice mapping which maps all the directions on the sphere to this one single image, and we can store all the pixel values and all the radiance values in a single image, which needs to be HDR, of course. So what we typically use it for in my domain is for rendering in augmented reality. So now I have a small bonus to explain how this can be used, how these kind of maps can be used for real-time rendering on the mobile devices in augmented reality. So initially, we need to have this kind of light probe, which we capture by our mobile device. And then on the same place, we can render these kind of objects. Here, this is the physical dragon, which is 3D printed, and this is the virtual dragon, which is rendered. And they should have consistent shadows. Maybe it's not that visible here, but also consistent reflection, and they should look that they belong to the same world because they have the same light. So how can we do this? We use, of course, our captured illumination, which we have here, for rendering. And how we do that rendering? We simply take every pixel, every incoming light direction here, and this is the radiance from every pixel, from the pixel I, let's say. We multiply it by the material function, which is called bidirectional reflectance distribution function, which tells us only how much light is being reflected from the incoming light direction omega I to the outgoing ray direction omega O. So it simply says how much light should be reflected. We multiply this by the cosine factor, which says that the reflection is dependent on how much the surface is tilted. So mostly the surface normal plays the role here. And then we sum up all the values from all the pixels, and we get our final radiance value for every pixel of the rendering. Now, if you think about this, this is quite a lot of calculation. If you have, for example, 1 megapixel high dynamic range environment map, and then we want to render again, let's say 1 megapixel image in our rendering. That means that's 1 million pixels times 1 million calculations. That's 10 to the power of 12, which is quite a lot of calculations, which we cannot do in real time and no way on mobile device. So what we need to do here, we need to pre-calculate some values. And the way how we do it, we start again from the same equations, and we think what we can pre-calculate here and store in some kind of special maps, which we call reflection maps. So firstly, we need to express our material function, and this one, we pick here the Fonck BRDF, which is the simple one, which consists of the diffuse term, which says how the light is reflected in the diffuse way, which is just a constant basically, and there's the specular term, which is again some constant, the color of the specular reflection, and the cosine factor of angle alpha. I will explain what that is, which is making this nice shiny reflection on the shiny objects. And how we basically substitute this back here into this FR term, and that splits us the sum to the two possible sums, which we can use to pre-calculate the two reflection maps. This one is called irradiance map because it contains only the diffuse reflection, and most of the terms are actually constant. This is constant here, this is our input map here, and only this is variable, the normal itself. So what if we recalculate it for every possible normal, such a map that convolves this cosine factor with our input map here, and we again store it in this kind of format, which we can access by the surface normal, and that tells us already the reflection of the diffuse surface. And that we can do, and we call this reflection map or irradiance map for the diffuse reflection. And then we can do the same for the specular part, which is here, which is a bit more complex. But again, here we have a lot of constants, like Ks is a constant, which we can take out in front of the sum. Then these two cosine terms get cancelled. This is again our input. And here is the only variable part, which is cosine to the power of n. This is not the normal here, this is the shininess factor, the n itself. So for different shininess of the materials, or different roughness factors of the materials, we need to pre-calculate different maps, which we access based on this angle alpha. And what the angle alpha is, that's the angle between the reflected view direction. So this is our camera ray, and this is reflected camera ray, and this is angle, oh sorry, this is one, and this is the angle between the reflected camera ray and the incoming light direction, so basically the one coming from here. And then we can parameterize this new reflection map by this reflected camera ray, because it contains the alpha itself and the incoming light direction. So let's say for every shininess or roughness factor, we pre-calculate a different reflection map, and then we can access it in real time for rendering. How does the calculation look? So this is the reflection map. You see it makes it a little bit blurry, and that's basically the result of convolution of the input map by the material function. And the material function, the kernel of the material has a different shape because it's dependent on the direction. Every pixel here represents one direction in the map, so it's shaped differently. And we simply do the convolution here, and we get this final reflection map. And if we calculate this for every material, it looks like this. This is the diffuse map or irradiance map, which is just the cosine convolution. And these are the different shininess up to the very shiny material here. And how can we then use it for rendering? The rendering is then very easy. We just do have the two texture reads. We read one value from the diffuse map and one from the specular map. That's this EV and ES. This one is read based on the normal of the surface, and this one is read based on the reflected ray direction, reflected view direction. And we simply multiply this by the material constant. So this is the specular color, this is the diffuse reflection color. So if our material is blue, it will reflect more blue diffuse color, as you see on this diagram here. And we simply sum them up. So the cost of this is simple two texture reads and two multiplications and one sum. That's very, very cheap and can be done very quickly also on the mobile devices. So this is a simple example of how that works, and it contains of two steps. The first one is the capturing of the light with the mobile device, and then subsequently rendering with this reflection map. So this is myself here. You see I'm rotating here with the mobile device with this tablet. By the way, I have a demo here with me, so afterwards, if you'd be interested, we can take a look together. And here I rotate completely around to capture the full 360 degrees of light. The light is being reconstructing because we do know the inverse camera response function here. And I cover here the full sphere. And then these reflection maps are being calculated, which takes around half a minute on the mobile device. And then we can use it for real-time rendering already. And you will see the real-time rendering. We need this kind of marker to know the position of the camera. And then the light from this place is used to render these objects. So it should be correctly reflected on the object. There is a more specular one, you see more light reflection there, or there is a diffuse one, where we combine these different material properties.
Virtual objects?
Yeah, these two are virtual, yes, the dragons are virtual in this case. But the light from that place is used to illuminate them. Yes?
So here, visibly, you printed some pebbles on an A4 sheet. Like I understood when it was on the carpet, but here it would seem that you have enough texture on the ground that you wouldn't need this kind of marker.
That's correct. We can use slant tracking to be completely markerless, but in the time when this was captured, the marker tracking had a little bit better quality. That's why we used it just to get more precise camera position. Yes, you have a question?
Your pipeline considers the first step in which you have your phone or your device and you're recording to reconstruct the sphere surrounding you. So like you have to estimate the pose of every frame.
Yes. But this one is a bit different. For this one, we do not use this kind of marker. We just use the inertial measurement unit of the foam, which uses the accelerometers to get the gravity, and which uses the magnetometer to get this kind of horizontal rotation. So we only use that to estimate the orientation of the device, and then we can project the image to this map, which is captured. So let's continue to the third category of method, which is, I think, the most interesting, and which is the illumination estimation. So imagine we have a single image of the environment, and we already want to estimate where the light comes from, given just this one image. And here I would like to show you results of our research, both with success cases and also with failure cases, so you can also see where we also failed. And our goal was here, having RGBD image, so not just the color, but also depth per every pixel. For example, you can have a Kinect or any other RGBD sensors to have this. And having this data, we wanted to estimate the main dominant light direction, like where the light comes from, even if it's behind the image, even if it's not visible in the image. So how we wanted to do it is to train a deep neural network. And for this one, we of course need some data sets, so I will speak how we captured it and created it. We also proposed some hole filling because many sensors do have holes in the depth images. And we need to remove then outliers and do some temporal smoothing, and we can achieve some nice light reconstruction there. So first, let's speak about data set. We use the combination of the real data set and the synthetic data set. For real data set, we capture this kind of device, this kind of images with a Microsoft Kinect device. And for the synthetic data set, we render these kind of simple shapes with the different positions of lights, and we had the ground truth image values also for that one. And then we had already our first attempt of creation of the network, which can estimate the light direction. So this was the first attempt, which actually didn't work well. So this is a failure case. But what was the idea was that we put our RGBD data here. We have some convolutional layers, which are typical in the neural networks for computer vision. Then we have some dense layers. And we wanted to have also second head here, which indexes the extrinsic camera parameters, so namely the position and orientation of the camera with respect to the marker. Then again have some dense layers here, combine these two data, and then get the final vector of the light. So basically x, y, z vector in the global coordinate frame. And of course this one failed. The reason was that to estimate this kind of vector in the global coordinate frame, having the extrinsic camera parameters was too complicated for the network, and the optimization simply couldn't find the correct gradient to optimize it. So we did some iterations here. Our first idea was to use a little bit more complex network because the problem was complex, and we used this residual network called ResNet, which allows for using really deep networks, for example, 55 layers. That's what we had, and that helped us a little bit to improve the performance. But the problem was still, so that was a good idea, but the problem was still that this network structure was very bad, and the reason was that this XYZ is still very difficult to relate to the global coordinate frame given the extrinsic camera parameters. So how can we solve this? That of course didn't work. And how can we solve this? We need to make the problem much, much simpler and simply estimate the light direction in the coordinates of the camera. So if we have our camera image, we should not care at all about the global frame, how the camera is rotated, but just have the light direction estimated relative to the camera orientation. And that helped a lot because now there was not needed for network to calculate any relation between the camera orientation and the world space, but it could directly estimate only the two angles, theta and phi, with respect to the camera. So these were relative light direction angles or relative to the camera orientation. And then knowing the camera orientation, we could also calculate the global rotation or global direction of the light. So this was a simple network which worked at the end very well. We had our RGBD input, having the rested layers, which allowed a deep network, then some dense layers, and at the end we just the network output two numbers, which is directly the theta and phi of the light direction.
Sorry, I missed the dimensionality of your data that you input in your neural net.
In this one or previous?
In this one.
This one, so RGBD is the image,
Yeah.
and it has RGB values per every pixel, but also depth values. So there are 4 values per pixel being input.
And so the output is phi and theta for each
Image. So you have one image, you capture it, and from that one you already get the theta and phi of the light direction, basically.
And how do you train? So you have ground truth.
Yes, we had ground truth light directions from the real world that we measured by the normal measurement device. And from the synthetic data, we knew this because this was rendered by given light positions. So we knew theta and phi. And we needed to recalculate this ground truth data to the camera space, of course, because now this operates in the camera space. Then we also had some extensions, how to modify this system. We thought about using only RGB data because depth is cumbersome, not all the sensors have it, but that one failed. This one didn't work that well, so apparently depth was important here. We tried to use only synthetic data set, no real data, and that worked for us because the problem was that our real data was not of a high quality. So high quality data is very important for deep learning, and we realized that our real world data is not that good, so we at the end decided only to use synthetic data. However, it has a pitfall that it is generally recommended to have a combination of the real data and synthetic data because there might be a big domain gap between synthetic and real, and if we train just with synthetic, it might not work very well in all the situations in real world. We tried zero mean normalization of the values of all the pixels in all the images. That worked pretty well for us. We also did hole filling in the depth data. That was also helping the result. And we tried to pose this problem as a classification problem. So imagine you have, let's say, 100 bins on the upper hemisphere of the light directions, and you want to categorize or classify your image that the light is becoming one part of these bins, one part of the direction. But that was not a good idea, and that didn't work at all. The previous example worked much better, that you directly estimate theta and phi for the angle. And we also tried random shuffling the input data set during training. That was very good, that helped a lot also to get better performance. This is our final network which we used. So here is the RGB image, which gets in the full resolution into the network. And then there are many convolutional layers which are residual. So there are these deep connections here, and that helps to prevent the vanishing or exploding gradients. So just many convolutions. The network is quite deep, it's 55 layers. And then at the end, just few fully collected layers which output to the two numbers theta and phi. So for every image, we can guess the dominant light direction here. And here are some results of that method. This is the input image, and this is rendering because that we can compare the direction of the shadow the best. This is the reference, the ground truth value. This is our value. You see it's a little bit off, and this is also some comparison method, which is also a little bit off in the other direction. And this is a back projection of our estimate. This is from our network to the omnidirectional image, which I captured by the other camera. And you can see here that it kind of correctly recognized where the window is in this image. And here a short video of how it works in real time. So what we see in the video, there is a real cactus plant, and I am again moving the light source here, and you will see the shadow moves, and then there are two digital objects, the dragon and the monkey rendered. And the shadows of these two are moving accordingly to the shadow of the real cactus. So this shows like how well the estimation runs. The estimation runs here in real time, so the network estimates all the time new values and are being fed to the rendering system. You can see that it's jumping a little bit. The reason is that the speed of estimation is around 10 frames per second. So it's not really high speed, but it's slowly moving. So what we learned from this, we learned that neural network can directly regress the light direction from the RGBD images. The estimates should be definitely in camera space, not in world space, and also quality of training data is very important. And now let's come to the final topic, which is also about light estimation, and this is part of our very recent research. And now the question is, can we use generative methods, can we use generative AI to generate the content of the light, about light in our real world, in a way that matches the real illumination scenario. And this is what we focused on. And for this one, we first, of course, need the data sets for our target scenes. So if we want to have a general method which works for any scenes, we want to have a lot of data from any scenes and also ground truth illumination for that one. In our case, we decided to go for estimation from human faces. So we created a human face database. I will show it also later. Then we need to have a way of controlling the generation. Typically, the generation of the images is being done by the stable diffusion methods. And we need to have a way how to control this stable diffusion generation in a way that it fits to the real world distribution of the light, especially the directional distribution. Then also the question is, what do we do with the text prompt? Because the stable diffusion methods very often have a text prompt in the input. And okay, let's come to the point how we did it. So we generated our own data set of the human faces, as we wanted our method to work on the human faces, where we point our camera to the human face, then it should estimate how is the light around this human. And we generated these synthetic images. All these humans here are non-existent, they are rendered. And for this, Unreal Meta-Human Creator is being used, which creates these very nice realistic faces. And we use the open and available HDR light probes, which you can download and use. And we used them to render and illuminate these faces with different human expressions, with different face types and different environments. And we rendered this by path tracing in Unreal Engine, and we created more than 100,000 images, which we could later use for training. So the second question was, how can we control the network? And for this one, we created the brightness estimation network, which can estimate the directional illumination around the person. And the idea was to use this kind of unit architecture, having a face image as the input, then downscale it by some holonotion layers, and have some latent vector in the middle, and finally upscale it back to the illumination image, to the HDR image.
And do you have skip connection between all the different scales? Or do you have, it's like auto-encoder-decoder structure? Do you have skip connection as well?
In this case, no. I think there were no skip connections. I hope, yeah. I think there were no, they were just this middle latent vector. And in order to do this, we first trained the autoencoder from the environment to the environment. So from the image to image itself, basically. And the reason for this was to train this latent vector in a way that it stores the illumination values, the directionality of the illumination in a way that we can reconstruct it back again. So we first created this autoencoder, and then we tried 3 different ways of training of our face to illumination estimation network, that we connected the face with this later part of the network, and we trained everything, the whole network again. The second one was that we fixed the decoder here, and we only trained this part, the encoder. And the third one was that we cut the decoder completely, and we trained to the latent vector, and we had the ground truth values in the latent space, so we could only train this part here. And from these 3, this one, the middle one, was working the best. So here are some results of this brightness estimation network. This is an input phase, this is a ground truth brightness, and this is what our network was estimating. So you can see that the highest brightness is in the values where the windows are, or where the dark areas are. There is also dark here in this estimated brightness, which worked well in this case. A little bit less better in this case. This is a real face image, and this is a ground truth environment, and this is our estimate. You see, fails to estimate any details, but it captures well the directionality of the sun itself. So there is a sun here, and that one was estimated correctly from this network. So now we would like to use some stable diffusion for generation of our panorama images. And what we did, we fine-tuned stable diffusion 1.5 to generate the panorama images like this. And we still had our question how we deal with the text, input text for the generation of the images. And our answer was to use the blip library, this library which can generate the text descriptions from the images. So we have our input image, and we would like to generate the text description, but not in a way, not in a very generic way, because it would tell us, of course, there is a face in the image. That's not what we were interested in, so we a little bit changed it and fine-tuned it here. And this description was only about the surrounding environment. So this blip tried to guess what is actually behind the person in a textual way. And then we could intake this text into our Stable Diffusion model and generate already the images which fit thematically to the background here. So these are the results of our Stable Diffusion generation for this input image, but that still does not contain the control by our brightness estimation network. So let's go to that point. This is our final architecture of the system for generation of the light maps based on the images and the Stable Diffusion. So here we have our input image, and then we estimate our brightness. This is the brightness estimate, which is maybe not that good in this case, but still at least guesses where approximately the light is. And this one is taken in to the Stable Diffusion by so-called control map. This is another network which can take another image and put it into the Stable Diffusion as the partial input. And this is then the result of the final estimate or the final generation. And here is some results of how it works. So this is the input and this is our output of the generation, and this is the ground truth. You can see it's still a little bit too far from for example, the mid part, but still the bottom and top are captured more or less. There is some snow, there is some bright areas on the top as well. There is one more parameter to be explained, which is called guidance scale. And this parameter controls how much the control map, how much our brightness image influences the generation. So if this guidance scale is higher, then we get more closer image to our estimate from the brightness. And if it's lower, then we get more generated image. And as you can see, if we have it like 0, then the generation is very nice, but the directionality of the light might not fit to the ground truth very well. But if we use this kind of parameter, for example, then we see the window is captured much better, and at the same time we have some details here. If we have too much, then we have just the same image as our estimated brightness, which lacks the detail completely. And that was the last part. So in summary, we can say that mostly for this light estimation and capturing methods, we assume distant light, and we definitely need high dynamic range images, and we can have 3 categories of methods to estimate light. First one is capturing, second one is stitching by multiple images, and the third one is by estimation from the main camera image. And that was everything. Thank you for listening.